Welcome to Computer Science 302 Precept 9 on Monte Carlo estimation. We would like to find statistics like the mean or the variance of our probability distributions for learning and prediction. We've seen that for many common distributions, these are simply functions of the parameters that we can look up or memorize. For example, if a random variable x is distributed as a binomial with parameters n and theta, then the expectation of x, or its mean value, its expected value, is n times theta, and the variance of x is n times theta times 1 minus theta. In many interesting cases, we don't know the distribution or its parameters. Sometimes we'll only have access to samples from a distribution pi of x, or perhaps we only know the distribution up to a constant. And in that case, we'll refer to this as pi star of x, and note that it is a constant c times pi of x. Using this information, we can still estimate the mean and variance and other quantities of interest using the Monte Carlo method. Let's look at the definition formally. Given samples for some distribution pi of x, we want to compute the mean of f of x for any reasonable function f. So you could imagine setting the function f to the identity, in which case we're getting the mean of the random variable as opposed to the mean of the function of the random variable. So recall that we can write this expectation over the distribution pi of x of the function f of x as simply the integral of f of x times pi of x integrated over the domain of x. This identity is sometimes called the law of the unconscious statistician because if you didn't remember what to do with the expectation of some function of a random variable, you might naively just think that you would do the same thing as you would normally, but putting the function over the variable. It turns out that that is actually the correct thing to do, hence the unconscious part, but actually the proof is non-trivial, and you can look it up if you're curious. Now, any such integral can actually be estimated directly from the samples. So as we can see, the integral, f of x pi of x dx is approximately equal to 1 over s times the sum from s equals 1 to s of f evaluated at each sample x, where each sample x comes from the distribution pi of x. We call this quantity the Monte Carlo estimator of the mean. Monte Carlo estimation has some nice properties. It's unbiased, meaning the estimator f hat, where f hat is referring to the summation before, which we have right here. The estimator f hat is the expected value of interest exactly. There's no additional bias garnered by our estimation procedure. That's not always true, but that is true in this case. So formally, we can simply write out what our expectation is. So note that we have this notation of a set of x's indexed by s. By the linearity of expectation, this simply becomes the sum of s equals 1 to big S of the expectation over pi of x evaluated at f of x. But since each xs has the same expected value under the function f, this is simply the expectation of interest. Another nice property that Monte Carlo estimation has is that its variance as an estimator decreases with more samples. Once again, calling the estimator the Monte Carlo estimator f hat, we can apply the usual operations, and noting that each x superscript s is independent, we end up with a summation of identical variance terms. And recall that when we pull a constant out of the variance, it squares. And so looking overall at the variance, we notice that picking up an extra s term for the sum, the variance of the estimator shrinks as 1 over s. We can see that with the 1 over s term, as s gets very large, the variance vanishes. Taking s to infinity, the variance goes away entirely. These properties show us that as the number of samples increase, our estimate f hat approaches the true value of the expectation of f of x. That's great. But notice that if we think about the standard error of the estimate, it only shrinks as 1 over the square root of s. This means that if we want to reduce our error by 1 over m, we must increase our number of samples by m squared. So taking m to be 2, we need 4 times the number of samples just to get 1/2 of the error in our estimator. This has led some to denigrate the Monte Carlo method, like Alan Sokol, who said that Monte Carlo is an extremely bad method. It should be used only when all alternative methods are worse. Nevertheless, in many cases, the Monte Carlo method is perfectly good enough, especially when we only need a rough idea of what the mean is going to be, rather than an exact, precise estimate. As an aside, notice that we can actually use this method to evaluate any arbitrary integral over some domain omega. Notice that if we think about the integral over omega of some function of x, f of x, we can introduce a new term, a distribution q of x. And this distribution q of x, notice that right here I've written it as just 1. All I've done is put the number 1 inside the integral. Nothing has changed. But rewriting this slightly as f of x over q of x times q of x dx, I've actually turned this into an expectation under x of the ratio f of x over q of x. So as long as we choose a probability distribution q such that the property q of x is greater than 0 for every x in omega, we can use this trick to evaluate the integral. Now, it seems that so long as we can sample, we're able to evaluate the statistics of a probability distribution. This is great for machine learning, and so now we need to discuss sampling again, because it is not as easy as it might seem in every case. So remember that we're looking at our Monte Carlo estimator, which is approximately equal to the integral of f of x times pi of x dx. And this estimate gets better as s increases, our number of samples. So what if pi of x is not something easy to sample from? So easy to sample is something that you can probably find in NumPy or some numerical computation package. Notice that if we think about some arbitrary weird distribution, pi of x, notice this one has strange bumps. It has no easy functional form that we can describe. We learned last week about inverse transform sampling. So inverse transform sampling gives us a way to go from samples u from a uniform distribution over 0 and 1 mapped through the CDF of a function back down to a point x of s. So we can find what point x of s we're interested in by simply looking at the inverse of the function big pi. So big pi here is the CDF, and notice that the CDF itself is an integral. It's an integral from minus infinity to x of pi of x prime dx prime, just the dummy variable. Notice though that we still have an integral hanging around. So if we can do this integral, then everything is fine. But often this integral will be intractable. So indeed, inverse transform sampling can be convenient, but because we still had to put an integral in there, we all know that integrals can often be really, really nasty. They're impossible to compute sometimes in closed form, and often quite hard even to approximate. So stepping back, we have a new tool, the Monte Carlo method, and this will let us figure out the mean and variance of potentially much more interesting distributions. Inverse transform sampling does let us do this, but it still requires us to be able to integrate pi of x, and also it requires us to always know the normalizing constant of pi of x. We can't simply know pi up to some constant. this can be difficult in real-world situations. The next technique we're going to talk about, rejection sampling, is a way to get around both of these constraints. So let's start with some intuition. Let's take some pi star of x, which, notice now, is just some constant times a normalized distribution pi of x. And let's think about drawing samples uniformly from the volume beneath the PDF. So by the volume, I mean quite literally the area under this curve. So if I were able to draw samples uniformly from this volume, it would have to have the correct marginal distribution. So if we imagine drawing samples uniformly according to the volume, anytime there was a peak, I would expect more samples to occur. And if I were then to draw a histogram of these samples, I would expect the histogram to look very much like this blue curve. So that's nice, but it's not obvious how we can simply draw samples from a volume like this. So the trick here is to choose some other distribution q of x. And we're going to choose this q of x so that it has a certain property. We will require that q of x is greater than pi star of x for any possible choice of x over the domain in which both have non-zero support. So we're going to sample from the distribution q of x, and then we'll throw the ones away that are above the blue curve. So the blue curve, again, is our unnormalized distribution, which is some constant away from the actual normalized distribution. So let's visualize this. So we've drawn a bunch of samples now from our easy to sample from q of x. Notice in this case I've chosen it to be a bell curve. You could also think of there being some kind of uniform distribution, but in this case the bell curve seems to match a little bit better. If we were drawing uniformly from the uniform distribution, we would have to throw a lot of extra samples away just because we have extra mass that's useless sitting above this distribution. So now that we've sampled from our q of x, we can throw away any of the ones that are above. And notice we're left with only samples that are inside the volume that we were targeting. So we've achieved what we wanted to in the first place, which was to sample uniformly from the volume. We can summarize this as the following algorithm. So we can choose a q of x and a c such that q of x is greater than or equal to pi star of x, which again is equal to c times pi of x. This is a bit of an art, and it's true that there are some very non-obvious choices here, so you have to have some sort of knowledge of at least this unnormalized function. But we are assuming that we know something about pi star of x, and so we can use that information to help us choose q. Then we're going to sample x of s from our q, and then we're going to do something which may seem a little unintuitive at first. We're going to sample a uniform random variate from a uniform which is scaled to be between 0 and the height of our function q, evaluated at x of x. So if we visualize that one more time, so we have some axis here, we have our strange, hard to sample from distribution, and then we have our easy to sample from distribution. In particular, this is going to be our q of x, and this will be our pi star of x. So step 3 is doing the following, and we can visualize it as follows. We're going to basically draw a line starting at 0 and going up all the way to the height q of x at this point s. Remember that our x of s is easy to sample because it came from q. When we get our u of s, it's sometimes going to be above the curve, and it's sometimes, in other cases, going to be below the curve. I'll give this point label s plus 1. Then we're going to apply rule 4. We're going to say anytime that u of s is less than or equal to pi star of x of s, we're going to keep x of s. Otherwise, we reject and go back to step 2. So this introduction of a u of s may seem a little bit non-obvious, but it's crucial that we have this extra source of randomness in order to ensure that we're only sampling in an unbiased manner from the normalized distribution pi of x. That's all there is to the rejection sampling algorithm. And if you have any questions, please tune in to our office hours / precept hours on Thursday and Friday, and we can address them there. Thank you very much for your attention.